So we just finished talking about electrons. Let's shift gears to talk about some of the chemical bonds that we'll see occurring between different atoms. So we touched on this idea of the octet rule, where the outermost shell, what we call the valence shell of electrons, can hold 8 electrons. And atoms, when that valence shell has 8 electrons, atoms are in their most energetically stable state. So it's kind of like their happy spot when they have 8 electrons in their valence shell. So really, most atoms are trying to achieve this stable state because they all kind of want to be like these noble gases, right? The noble gases are the ones that are not reactive. They're not reactive because they don't need any other electrons in their valence electron shell, in their outermost shell. But if an atom doesn't have that full octet in its outermost shell, or the 2 if it's a small atom like hydrogen, if its outermost shell can only hold 2, if that outermost shell is not full, it's not complete, atoms will form chemical bonds between other atoms in order to achieve that stable state of having an outer shell. And so we're going to talk about the different ways that atoms form chemical bonds to achieve that state. So chemical bond is interactions between electrons of different atoms that creates a force which holds the atoms together. That force that holds the atoms together then keeps them physically close together and combines the atoms into what we call molecules or compounds. So for example, water, H2O, 2 hydrogens, 1 oxygen, is the result of a chemical bond occurring between 2 hydrogen atoms sharing their electrons with oxygen. And that process of sharing their electrons keeps those atoms together to form the molecule that we call water. But how are these bonds formed? Chemical reactions, which we'll cover in another video, are how bonds are broken and formed between atoms. So chemical bonds represent a form of stored potential energy, meaning that it takes energy to make the bonds, and we can release that energy when the bonds are broken. And that's basically what happens when we burn gasoline, or when we eat food. We're breaking the bonds down in our food molecules to release the energy that's there and convert it to a different form. So for example, let's say we have a propane stove. So when propane, which is this molecule right here, and oxygen react, when propane and oxygen gas react, we can then break the bonds in that propane molecule and create carbon dioxide and water as a byproduct. And that process of breaking up these bonds in this propane molecule, breaking up the bonds between the carbon atoms, between the hydrogen atoms, not only does it change the structure of the molecules, it rearranges the structure of these molecules to give us CO2 and water, but it also releases heat and light, energy, because there is stored energy between the bonds of these carbon and hydrogen atoms. So now we're going to talk about what's actually happening in these different types of chemical bonds that are formed. Chemical bonds are formed when atoms are either sharing electrons, or they're being held together by electrical charges due to differences in their overall charge, which still involves the swapping of electrons. So we're going to talk about 2 main types of bonds, ionic bonds and covalent bonds. So covalent bonds, co meaning to share, and valent meaning their valence electrons, their outermost electrons, right? So covalent bonds form when atoms are sharing electrons in order to complete their outermost shell, in order to complete their valence shell. These are very, very strong bonds, and they can hold a lot of potential energy, meaning that it takes a lot of energy to also break these bonds as well. Covalent bonds can be single, double, or triple, depending on the number of pairs of electrons that are shared. So for example, between carbon and hydrogen right here in this glucose molecule, this line represents a covalent bond right here. And because there's only one line between those 2 atoms, that means they're only sharing one set of electrons, so we call that a single bond. Whereas over here in our glucose molecule, right here between carbon and oxygen, there's 2 lines. Those 2 lines, that double line represents a double bond, which means that there are 2 pairs of electrons being shared between carbon and oxygen right here. And over here in nitrogen, 1, 2, 3 lines between the 2 nitrogen atoms, so it means they're sharing 3 pairs of electrons. So the more pairs of electrons that are being shared, the more energy is being stored in that bond, and that means that the more energy it takes to break up that bond. So again, back to our water molecule, right? So 2 hydrogens, 1 oxygen. So oxygen 1, 2, 3, 4, 5, 6 in its outermost shell, in its valence shell, it needs 8 to achieve that stable, energetically stable state. Hydrogen needs 1, hydrogen needs 1. So what's going to happen is that this electron right here and this electron right here are going to be shared between hydrogen and oxygen. And this one right here and this one right here are also going to be shared between hydrogen and oxygen. So it's going to end up looking like this. So now these electrons are spending time with both oxygen and hydrogen, and these electrons are spending time with both oxygen and hydrogen. What makes it seem as if oxygen has a full octet, and now hydrogen has a full valence shell as well. Because these two are going to spend time with oxygen and around hydrogen. They're being shared. Okay, but because they're being shared, it's going to hold those two atoms in close proximity together, which forms a molecule. Electrons are being shared, covalent bond. We have 2 flavors of covalent bonds. We have nonpolar covalent bonds and polar covalent bonds. Nonpolar is when the electrons are shared equally. So when atoms have a certain amount of pull that they have on shared electrons, we call that their electronegativity. When atoms of the same electronegativity are sharing electrons, they have an equal pull, which means the electrons are going to be distributed 50-50. Okay, so it means that there's no difference in the amount of time each atom gets the shared electrons. So as long as the electronegativity of the 2 atoms are the same, there's going to be a nonpolar bond, meaning the overall charge to the molecule, there's going to be no difference in the charge of the different regions of the molecule. So for example, iodine will readily bond with itself, but because it's the same atom, same element, iodine has equal electronegativity, so there's an equal pull on those shared electrons. So the electron density is spread out evenly between those 2 iodine atoms. Compared to polar covalent bonds, in polar covalent bonds, the electrons are not shared equally. So oxygen is a very highly electronegative atom. So it means it has a strong pull on shared electrons. So when oxygen bonds with an atom that has a lower electronegativity, like hydrogen or carbon, the electrons that are being shared in that covalent bond with oxygen will tend to spend more time around oxygen than they will the less electronegative atom. Remember, electrons are negatively charged, so that means that in a polar covalent bond, due to the unequal sharing of electrons, one part of the molecule starts to get a slight negative charge. That's what's represented here by this lowercase delta, the Greek letter delta, delta negative. And one part of the atom, one part of the molecule gets this like positive charge. So it's going in here with this delta positive. So because the electrons are spending more time with oxygen, they're not getting their fair share of time around hydrogen. Electrons are negative, more negative time with those electrons. Oxygen has a slight negative charge, and hydrogen has a slight positive charge. So the molecule itself is what we say is a polar molecule because it's built out of polar covalent bonds, unequal sharing of electrons. The other type of chemical bond is an ionic bond, and this is when cations and anions, remember we talked about atoms can form ions when there's a different number of electrons than there are protons, the atom will have a charge. So ionic bonds are formed when we get a cation and an anion that have different electrostatic charges are come into contact with each other. So these are strong bonds, but they can often dissolve in water because water is very polar. Ionic bonds are often the result of donating and accepting electrons. So let's say, for example, this example here, there's no names to these atoms, but this atom has only 1 electron in its valence shell, so it's not going to be able to find 7 to fill that up. It's probably not an option. But if we were to get rid of this 1 electron in its valence shell, that would reveal the next shell lower down, which remember is already full. So this atom that only has 1 in its valence shell will readily donate this electron, transfer that electron to another atom. Typically, atoms that have a strong pull on these electrons have only maybe one or two open spaces in their valence shell. So like this atom right here only has one empty space in its valence shell for those electrons. So it has 7 electrons. So it will readily accept, it's more than happy to accept this one little electron. But what happens when this atom gets rid of its electron, it becomes positive, it becomes a cation. When this atom accepts that donated electron, it becomes an anion, it has a negative charge. So now they have two different opposite charges, positive and negative, that creates an electrostatic force that keeps those two atoms together. That's what we call an ionic bond. So things like sodium chloride, table salt, is formed through the exchange of electrons from sodium to chlorine. And ionic bonds often form regularly ordered crystals that have a very distinct crystalline structure to them, and they're often called salts. So if you see something where its chemical name is a salt, that doesn't mean it's just sodium chloride, that's just a general term used to discuss any sort of molecule that's formed through an ionic bond. Quick review, different overview of the different bonds and their difference in electronegativity. So in nonpolar covalent bonds, there is no difference in the electronegativity between the two atoms. The electrons are shared equally. In polar covalent bonds, there is a slight difference in electronegativity, and whichever atom has the greater electronegativity force gets the electron for a greater amount of time, which gives it a slight negative charge. And then the atom that gets less time with those shared electrons has a slight positive charge. All the way at the other end of the spectrum, where there's no sharing of electrons, but there's a transfer of electrons, the atom that gained that electron has now an anion, it's a negative charge, and the atom that lost that electron, gave up that electron, has a positive charge. So this is the extreme end of the electronegativity spectrum. So a couple other bonds, these are not bonds that occur between atoms. Hydrogen bonds and dispersion forces, which we're going to talk about now, are weak bonds that occur due to attraction between differently charged regions of a molecule. So for example, hydrogen bonds are named because in water, hydrogen is slightly positive because it doesn't get as much time with that shared electron. That slight positive charge on that hydrogen molecule, on that hydrogen atom in the water molecule, makes it attracted to the slight negative charge of an oxygen atom of a different water molecule. So they will form a weak bond, a weak attraction between the partial positive hydrogen and the partial negative oxygen. And this actually causes water molecules to kind of stick together, which you may not have ever realized. This is why water can flow. This is why you can drink through a straw, because those water molecules are being kind of held together by these hydrogen bonds. So hydrogen bonds also help to keep things like DNA together. The two sides of a DNA molecule, they're held together by hydrogen bonds between the different bases. Okay, between a slight positive and a slight negative charge, that's going to have enough of a force to keep those two sides together. The other kind of weak force between atoms or molecules is what we call dispersion forces, and these are caused by their slight variation and fluctuations in the distribution of electrons around an atom, and this can lead to very slight, short-lived differences in polarity within the atom itself. So electrons can be equally distributed around the nucleus, or sometimes, just due to a random chance, we might have more electrons on one side of the atom than the other. So whatever side of the atom has the electrons or happen hanging out with at that point in time will get a slight negative charge, and the other side will be slightly positive. Okay, so when there's an unsymmetrical distribution of the electrons, that means now that this atom is kind of polar, right? So this slight positive charge to the positive side of the atom will be attracted to anything that's stealth negative. So these are often short-lived, very weak, and they're only really come into play when molecules or atoms are very close together.